Hello, and welcome to Team 50's analysis of the effectiveness of Rochegard's smog-free towers and our recommendations for reducing pollution. To highlight the issue, Hong Kong, China has been experiencing poor air quality for multiple decades. While they have tried implementing a variety of potential solutions, the pollution levels are still having a dramatic impact on their economy and lifestyles. It was estimated that in 2013, air pollution caused 1.4 trillion US dollars worth of health-related costs from things like hospital admissions due to respiratory issues and loss of labor in China alone, and 5.5 million premature deaths worldwide. Hong Kong's Environmental Protection Department is searching for a solution that is efficient, cost-effective, and sustainable, with the most prominent currently being the use of smog-free towers. The particulate matter that is being measured to determine the effectiveness of Rochegard's design are PM2.5 and PM10 particles. Both of these are inhalable particles that have varying diameters. Any particulate below 2.5 micrometers is considered PM2.5, and any particulate that is between 2.5 and 10 micrometers is considered PM10. To begin our evaluation and analysis, we determined the overall objectives, which included determining the effectiveness of the smog-free tower design using evidence not collected by Rochegard and his collaborators, as this could obviously be biased or incorrect. We also needed to identify problems that could arise from or associated with scaling up Rochegard's smog-free tower design, and brainstorm solutions to any sustainability issues that exist due to prolonged use of smog-free towers. Finally, we needed to research and locate other potential solutions that were capable of reducing pollution and compare the effectiveness of these technologies to the smog-free tower to determine the best solution to the issue. To start off, we completed a myriad of project management items, including a Gantt chart, to ensure we had accurate time management and were making progress towards the completion of the analysis, a work breakdown structure to fully understand every aspect of the problem, and a needs-finding table to grasp what was expected of us by Hong Kong's Environmental Protection Department, and to create values to compare our final model to. We also completed research on various topics that have impacts on the smog-free towers by looking into subjects like the economic consequences of air pollution, the World Health Organization air quality guidelines, and the current air quality in Hong Kong.
Once the project objectives were determined, we moved on to the methodology or the model code that gave us needed evidence to determine if this type of technology was truly effective. This methodology included coded inputs such as particle density and particle diameter, vertical distance of the particle, the area of the panel, and time. Additionally, with these inputs, we were able to calculate 4 forces that were assumed to be the only forces acting on each particle, that being gravitational force, buoyant force, electric field force, and drag force. And with these calculations, we were then able to find the outputs such as velocity of the particle, position of the particle, and the forces acting on the particle. Now, in order to gain a better understanding of how to make these calculations, we needed to make various assumptions. The main assumption being that each particle is moving solely in the vertical direction. In other words, there is no wind, there is no horizontal motion of the particle. Additionally, each particle was assumed to be a sphere. This made it very easy for us to find the volume of each particle and the number of particles that the technology would be affecting, as it could be calculated just through the diameter of each particle. Additionally, we assumed that every particle was nitrogen oxide, which is the most commonly seen or known particle in smog. This also has a positive charge, making it easy for us to assume the charge of each particle. Additionally, through research, we were able to assume the constants of drag, of air resistance, fluid viscosity, and particle density through nitrogen oxide. Additionally, we needed to make various assumptions within our needs finding table to determine accurate constraints and criteria for this project. Some of the needs being the need to remove haze from the surface air or to remove dust from the surface air, being successful long term, being appealing to look at, and making air cleaner in large spaces. Overall, with these assumptions, we were able to come up with effective modeling data that allowed us to make conclusions upon this technology.
Once our team had a good understanding of the physical properties affecting a particle that would be moving within our smog-free tower system, we were able to translate those physical ideas into a code that modeled the situation for a specific particle in our system. Doing this was incredibly valuable to our team because it allowed us to analyze the effect of different changes to the system on the motion of the particle and subsequently determine which factors were most important for the final smog-free tower design. To create this model, we took 4 forces that would affect the particle: gravitational force, buoyant force, electric field force, and drag force, and made 4 user-defined functions within the code of our model to represent each of them. Each user-defined function would calculate the force that was experienced by the particle due to that force, using different inputs that could be defined by the user. Once we had all 4 of these force functions created, we were able to combine them into one larger equation that would allow us to solve for the acceleration of the particle due to those forces using Newton's second law. Once we had that big equation, we were able to use Euler's method to solve it for both the velocity and the position of the particle as over an interval of time. Once we had that information, we were able to subsequently use Cotter's method to determine which factors and which inputs to the model itself were the most impactful in changing the motion of the particle.
Through the code that we created, we were able to get a graph that shows the velocity of the single particle over time. You can see here that it is a linear graph, which is correct by our metrics. Given the minimal buoyancy and drag forces that are exerted on the particle due to its size and mass, both of these forces are somewhat negligible. The other 2 forces are gravitational force and electric field force. Both of these are taken into account through the model, and both have non-negligible impacts on the particle. The electric field force, however, does have the biggest impact on the particle as a whole. The charge is experiencing constant acceleration from the electric field force due to it not changing its mass throughout the process. This therefore makes the graph linear for velocity. When we were conducting these tests with the code, it was confirmed by the code that the acceleration that the charge feels would be significant in comparison to what larger objects would feel in the same electric field. Due to this extremely small mass that the particle has, it will accelerate much quicker and travel further in the same amount of time. The code was then used to conduct a Cotter's analysis of particle diameter, panel area, and charge. It was found that the particle diameter and panel area had the biggest effects out of the 3. Both of these were very similar, but the data collected showed that they have a higher sensitivity than charge as a whole. Therefore, we know that having smaller particles and larger panel area will allow the tower to work best. As a team, we are recommending that Hong Kong move away from fossil fuels and more towards clean energy as a whole. This is a sure way to reduce the amount of particulate in the air. These clean energy solutions, such as solar power and wind power, can also be integrated directly into the next recommendation that we have: smog-free billboards. Smog-free billboards work in a very similar way to smog-free towers. However, they are up in the air higher and therefore can take up more space. These billboards can also include clean energy collection devices on the top, which will provide the charge plate inside the billboard with power, making it more cost-effective and energy efficient. The other benefit to this is that there could still be advertisements on these billboards which would be bought by companies, which would therefore help to reduce the amount of money the government is spending on these devices. For these billboards to be most effective, location matters. They should be placed in the areas where pollution levels are the highest, which is along highways, along coastlines, and near factories. The final recommendation that we have come up with was to conduct further studies on the effect of weather patterns on the smog-free billboard idea. Currently, there is not much research that has been done, And as a team, we are unsure of how the billboards would work with the weather. If additional studies could be done to improve the knowledge base surrounding the smog-free billboard idea and weather due to the difference in altitude and location from the original smog-free tower idea, in the end, we should be able to figure out whether or not this is a viable alternative.
Generally, the smog-free tower technology is a viable solution to reduce the amount of particulate matter in the air. By powering these towers with clean energy sources, such as solar panels or wind power, it's possible to create a sustainable source of smog control that can help Hong Kong reach its air quality goals. Additionally, by carefully placing the towers at locations where particulate matter concentrations are the highest, the effects of this technology can be maximized. Although other measures need to be taken in addition to implementing the smog-free tower in order to achieve the World Health Organization's strict air quality goals, there is definitely a role for this technology to play in creating clean air for the future.